everyone. Let us continue with our discussion on semiconductor physics. Today we will be discussing about carrier transport, how the carriers are moving inside a semiconductor and how the current is being generated due to the transportation of carriers inside a semiconductor. There are two types of carrier transport, drift and diffusion. Today we will be concentrating on diffusion. Before going into the diffusion process, let me tell you what are the carriers inside a semiconductor. There are two types of carriers inside a semiconductor. The first one is electrons which are negatively charged. Then the second one is holes which are positively charged. Now you see what are the different process or transport process involved in semiconductors. There are two types of carrier transport in case of semiconductor. One is diffusion and the second one is drift. And as there are two types of carrier transport, we are having two types of current components in a semiconductor. So these two types of carrier transport, they result in two types of currents, that is diffusion current and drift current. Let us first understand what is diffusion. All of you must be using perfume, right? When you are spraying the perfume at one corner of a room, the person standing at the other corner can also smell the perfume. How it is happening? That is due to diffusion. Let us consider one more example, that is incense sticks. Though we are using the stick at one place, the smell spreads all over the house, right? So these are some of the examples of diffusion. What happens in case of a semiconductor? Here, this is a semiconductor I have shown over here. These red dots over here are carriers, that may be hole, that may be electron. And here if you can see, the number of carriers per unit area, that is very high as compared to the right hand side. So this left hand side, I can tell that the concentration is very high. That's what this region is with higher concentration. Coming to the right hand side, the carriers per unit area is very less as compared to the left hand side. So this area is having lower concentration. So here, what happens, like in current pandemic situation, all are moving away from the crowd place, right? Here also, always the carriers, they try to move from a higher concentration region to a lower concentration region. If we allow the movement of the particles or the carriers inside the semiconductor, they will move from higher concentration region to lower concentration region. And this is known as diffusion. So in this process of diffusion, the carriers always move from a higher concentration region to a lower concentration region. Why these carriers are moving from higher to lower concentrations? This movement of the carriers occurs due to the difference in the carrier concentration, because on the left hand side, what we have seen in the previous slide, the concentration was more on the left hand side. That's what the carriers, they move to a lower concentration region, that is towards the right hand side. So the difference in carrier concentration leads to carrier movement. The carrier move from higher concentration region to lower concentration region, and the carrier flux density. What is this carrier flux density? That is carriers flowing per unit area per unit time. The number of carriers flowing per unit area per unit time, that is known as carrier flux density. This carrier flux density, they depends on concentration gradient. What is concentration gradient? That is the change in concentration of carriers with respect to distance. So as we are changing the position, how the concentration is changing, that is measured by concentration gradient. And the carrier flux density, that depends on concentration gradient. We have seen that the carrier flux density, that depends on the concentration gradient. And there are two types of carriers in a semiconductor, so we will calculate both the electron flux density and hole flux density. First we will see electron flux density, that is the number of electrons flowing per unit area per unit time. I am representing the flux density of electron as phi n of x. Here x is the position where I am going to calculate the carrier density, and n over here it represents, this is for electron, that is the electron flux density. This is proportional to dn by dx. This is nothing but the carrier concentration gradient, and n over here again it represents the electron concentration gradient, and x is with respect to position. So this electron flux density depends on the electron concentration gradient. If you remove the proportionality sign, I'll get this dn over here, that is a proportionality constant, and this negative sign shows that the carriers move from a higher concentration region to lower concentration region. That means this gradient is in a decreasing direction. So that's what this sign is negative over here. So phi n of x is equals to minus dn of x by dx, and this dn is known as electron diffusion coefficient. Similarly, if we will calculate the whole flux density, that is phi p of x will be equals to minus dp of x by dx. This is the whole concentration gradient. dp is whole diffusion coefficient. Again the negative sign is because of the decrease in concentration gradient, because the carriers always move in a direction where the concentration is decreasing. Now let us calculate the current density. What is current density? We have seen the carrier flux density, and always current flows in a circuit due to the movement of carriers. So current density is the diffusion current crossing a unit area per unit time. Here I have taken diffusion current because we are considering now only the diffusion process, but at the end of the day we will be considering both diffusion and drift. So the current density is the amount of current flowing per unit area per unit time. And how we can find out this current density? That is charge into particle flux density. Whatever the carriers flowing per unit area per unit time, we have to consider that is the carrier flux density. Then we have to multiply that with the amount of charge of a single carrier, and from that we can find out the current density. This is the general formula for calculating the current density. First we will do it for electron, then we will see it for hole. So for electron, what is the current density due to the transport of electron in the process of diffusion? That is given as Jn diffusion, and this n over here it represents that this current is due to the flow of electrons, that is equals to minus q. All of you know that the charge of an electron is equals to minus q. So it is minus q into this is the carrier flux density or electron flux density, what we have just seen in the before slide. So it is minus dn by dx. Multiplying both this minus and this minus, they will become plus. So it is q dn by dx. This is the contribution to the current density due to the electron diffusion. Coming to the whole current density, this is Jp diffusion. This P represents that this current density is due to holes, and diffusion means this is the current density coming from diffusion of hole, is equals to charge into carrier flux density. Charge is plus q over here because hole are positively charged carrier particles. So it is plus q, and this is the whole flux density. So multiplying these two, we will be getting the current density due to diffusion of hole is equals to minus q dp by dx. We have seen that there is flow or the diffusion of electron and hole depending on the concentration gradient, and we have calculated the current density due to diffusion of electrons and holes. Then what is the total amount of diffusion current? That is, J diffusion is the sum of the diffusion current due to electron and diffusion current due to hole. So if you substitute the values over here, I can obtain that the diffusion component of the current density is equals to q dn by dx minus q dp by dx. Here this is the total current density due to diffusion, and this is the current density due to electron diffusion. This one is the current density due to hole diffusion. We have seen that how due to diffusion of electron and holes the current is being generated and what is the expression for that. In the next class we will see the second transport, that is drift, and what is the component of current we are obtaining from drift. Today we will stop here. Thank you all. Have a good day. Don't forget to like, share and subscribe my channel. Thank you once again.